Something out past Pluto is not staying silent tonight. A machine older than many parents is still listening in the dark. And from beyond the sun's protective shell, a thin, hidden note keeps rising out of the black. It is not a voice, not a warning, and not what scientists expected to find. If stories like this pull you in, subscribe and stay close. This is for people who want the real mystery, not the fake drama. Because space is strange enough without anyone making it louder. Voyager 2 began as a metal traveler with a short job and a small deadline. NASA launched it in August 1977, back when computers were weaker than a cheap phone today. The plan was simple on paper and wild in real life. Fly past giant planets, send pictures home, and survive a few years. Instead, it kept going, kept talking, and slowly turned into one of the greatest witnesses humanity has ever built. Most people know Voyager 2 as the spacecraft that visited Jupiter, Saturn, Uranus, and Neptune. It remains the only human machine to fly close to Uranus and Neptune, which already gives it a strange kind of fame. But those planet visits were only the first act, like the opening chapter of a much longer book. The real surprise came later, when the planets were behind it and the empty dark ahead started answering back. To understand why this matters, you have to picture the sun as more than a bright light in the sky. The sun is also throwing out a stream of charged particles all the time, like a non-stop wind moving in every direction. That stream pushes outward and builds a huge bubble around the planets. Scientists call that bubble the heliosphere, but in simple words, it is the sun's protective zone. Inside that bubble, Earth and the other planets live under the sun's influence. Outside that bubble, space belongs more to the galaxy than to our star. That outside region is called interstellar space, which simply means the space between stars. It is not a clean, empty void at all, but a thin ocean of particles, magnetic fields, radiation, and old debris from dead stars. For years, researchers wanted to know exactly where the sun's bubble ends. They knew there had to be a border where the outward solar wind finally loses its fight. That border is called the Heliopause. It is not a solid wall you can crash into, but a changing frontier where one space environment gives way to another. Before Voyager reached that frontier, scientists had expectations that sounded neat and orderly. They thought the boundary would be easier to define, and that the space just beyond it would be calmer in some ways. They expected differences, yes, but also a kind of clean handoff from the sun's domain to the galaxy's domain. Space, as usual, had no interest in being neat for human minds. Now the story gets sharper. On November 5, 2018, Voyager 2 crossed the heliopause at about 119 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, so Voyager 2 was about 119 Earth-Sun distances away. That is roughly 11 billion miles from Earth, far beyond Pluto, deep in a place no working spacecraft had truly sampled before. Voyager 1 had crossed that boundary first in 2012. But Voyager 2 carried a working plasma science instrument that Voyager 1 no longer had when it made its crossing. That mattered a lot, because it let scientists compare what the two spacecraft sensed in different places and at different times. For the first time, they were not trusting one lonely clue. They had a second witness. When Voyager 2 approached the boundary, its readings changed hard and fast. The solar wind speed dropped steeply. Its instruments stopped seeing the outward flow from the sun the way they had before. At the same time, the count of cosmic rays, which are high-energy particles from beyond our solar system, jumped and stayed high. That was the first big pattern. Scientists expected a change, but the data made the crossing feel more real than theoretical. The sun's own particles fell away. The galaxy's particles rushed in. Voyager 2 was not just far from home, it was standing in a different neighborhood. But then came the part that gave headlines their favorite word: mysterious. Scientists were not only measuring where Voyager 2 was, they were also hearing, in data form, signs of a strange frequency in the plasma around it. Not music, not spoken sound, but a repeated signal hidden in charged gas. This is where a lot of people get confused, so let's slow it down. Space is too empty for sound to travel the way it does in air. No one is holding a microphone out there and hearing a haunted whistle in the normal human sense. What Voyager detects are plasma waves, tiny electrical and magnetic changes that can be turned into sound for us later. Plasma is a gas whose atoms have lost electrons. That means the particles carry electric charge, and charged particles can move in patterns and waves. When those waves shake the electrons around them, the electrons respond at certain frequencies, And by measuring those frequencies, scientists can work backward and figure out the density of the space around the spacecraft. That is the key to the whole mystery. The frequency itself is not important because it sounds creepy. It matters because it reveals what the invisible material between stars is doing. It is like hearing the pitch of a bell and realizing you can estimate how big the bell is without ever seeing it. Voyager 1 had already helped scientists find a faint, steady plasma hum in interstellar space. Researchers described it as very weak, very narrow, almost like one thin tone holding on in the dark. Some compared the background of interstellar space to gentle rain, with solar eruptions acting like sudden lightning bursts. That changed how scientists thought about the so-called quiet between the stars. Voyager 2 did something just as important. It confirmed that the region beyond the heliopause really does carry the kind of plasma behavior scientists were trying to map. Its plasma wave instrument and other sensors showed that the density outside the heliosphere jumped compared with the density inside. That means the empty dark beyond the sun's bubble is not empty in the simple way many people imagine. Here is one of the numbers that makes researchers sit up. Before crossing, one of Voyager 2's last plasma density readings inside the heliosphere was about 0.0044 particles per cubic centimeter. After crossing, on January 30th, 2019, Voyager 2 measured about 0.039 electrons per cubic centimeter in interstellar space. Those are tiny numbers, yes, but the jump was dramatic, close to an order of magnitude. In normal life, a cubic centimeter is about the size of a small sugar cube. So imagine less than a grain of dust worth of material in that little space. That is how thin this region is. And still, even in something that thin, the difference was strong enough for Voyager 2 to detect and for scientists to trust. This matters because density tells a story. It tells scientists how tightly matter is packed, how waves move, how magnetic fields behave, and how the sun's giant bubble presses against the galaxy. It helps answer a much bigger question, too. How well does the heliosphere shield Earth and the rest of the solar system from dangerous incoming radiation? That shielding is not some small side detail. Voyager data suggests the heliosphere blocks a large share of cosmic radiation. In plain words, our star does not only give us light and heat, it also builds a huge protective zone around us. And Voyager 2 is one of the only machines ever sent far enough to test how that shield actually works. Now hold on to this next part because it is where the mystery deepens. Scientists expected interstellar space beyond the boundary to be colder and denser than the plasma inside the heliosphere. Voyager 2 did confirm that basic idea, but it also showed signs that the plasma just outside the heliopause was slightly warmer than expected and likely compressed. That is strange. If the handoff from one region to the next were simple, the numbers might have looked cleaner. Instead, the data hinted that the boundary is messy, squeezed, and disturbed on both sides. Voyager 2 also saw a slight increase in plasma density just before the crossing, so even the inside edge of the sun's bubble looked compressed, as if both sides were pushing harder than expected. If you were surprised by that, you are in good company. Scientists were surprised too. Did you expect the edge of the sun's influence to act more like a rough shoreline than a smooth border? If this part hooked you, tap like, subscribe, and tell me what you think that boundary should feel like if you could stand there. Another surprise came from the magnetic field. Many researchers expected the magnetic direction outside the heliopause to shift in a clear and obvious way. That would have made the border easier to read. Instead, Voyager 1 had already found something odd, and Voyager 2 confirmed it. The magnetic field just beyond the heliopause appeared nearly parallel to the field inside. That sounds technical, but the meaning is simple. The two sides of the border looked more lined up than many scientists had guessed. With only Voyager 1, maybe that could have been a weird local accident. With Voyager 2 seeing a similar pattern, that explanation got weaker. It started to look like the boundary itself behaves in a more organized and surprising way. Then there is the leak. One Voyager instrument suggested that a trickle of particles from inside the heliosphere slips through the boundary into interstellar space. So the heliopause is not a perfect seal. NASA scientists even compared the heliosphere to a ship and the outer shell to a hull that might be a little porous. That means our protective bubble may be strong, but it is not fully closed. Voyager 2's path made that idea even more interesting. Voyager 1 crossed near what scientists describe as the front of the heliosphere, relative to its motion through space. Voyager 2 crossed closer to the side, or flank. That flank may be more porous than the front. So the same border may not behave the same way everywhere. This is why a mysterious frequency matters more than it first seems. The signal is not just a cool soundbite for a headline, it is part of a map. Every change in tone, density, and particle flow tells scientists what the boundary of our cosmic home is shaped like and how it reacts under pressure. A lot of dramatic posts online make this sound like Voyager 2 found an alien broadcast. That is not what NASA confirmed. The signal is better understood as plasma behavior in the interstellar medium, the thin, charged material between stars. The mystery is real, but it is a physics mystery, not a movie scene with hidden messages in code. And honestly, that truth is even better. Because if space between stars can hold a constant background hum, if the sun's border can be compressed, aligned, and slightly leaky, then the galaxy is more alive than the old cartoon version. Not alive like a creature, alive like weather, motion, pressure, and structure moving through darkness we once called empty. There is another twist most quick summaries miss. Voyager 2 is beyond the heliosphere, but that does not mean it has fully left the solar system in the broadest sense. The sun's gravity still reaches much farther out, into a huge distant region called the Oort cloud. That cloud may begin around 1,000 astronomical units from the sun and stretch tens of thousands of astronomical units farther. So yes, Voyager 2 is outside the sun's protective bubble, but no, it is not yet beyond every part of the solar system. That sounds like a tiny detail, but it changes how you picture the mission. Voyager 2 has crossed one border, not the final border, and even that one border turned out to be stranger than expected. That is one reason the phrase, "just detected," can be a little misleading. The discovery is not brand new in the way a live breaking alert sounds. What is happening is that scientists keep studying the data, comparing the two Voyagers, and sharpening the picture. The mystery grows clearer over time, not because the signal is fake, but because the frontier is hard to read. Voyager 2 also reminds us how fragile exploration really is. The spacecraft launched in 1977. Its systems were never expected to be running this far into the future. Every bit of power matters now, and every instrument that remains active is living on borrowed time. NASA engineers have had to make painful choices to keep Voyager 2 alive. As the spacecraft's electrical power slowly drops year by year, instruments get shut down to save energy. The goal is simple and heartbreaking at the same time. Turn off enough science to keep doing science a little longer. In late 2024, NASA shut off Voyager 2's plasma science instrument to save power. That is the same kind of instrument that helped reveal the plasma environment around the Heliopause. Then, in 2025, another science instrument on Voyager 2 was turned off as part of the same effort. The ship is still sailing, but its lights are being dimmed one by one. Think about that for a second. A machine built in the 1970s crossed into interstellar space, measured a strange, hidden frequency in charged gas beyond the sun's bubble, and then had to survive on a shrinking electrical heartbeat. That is not just engineering. That feels almost like stubbornness made of metal. And still, even with fewer instruments, Voyager 2 keeps teaching us. It keeps sending back signals across billions of miles. Those radio messages take many hours to reach Earth. By the time a message arrives, the spacecraft has already traveled farther into the dark, and Earth has spun through another long stretch of night and day. That delay alone changes the feeling of the mission. Nothing is instant. No joystick, no quick fix, no live repair. When engineers send a command, they wait. When Voyager responds, they wait again. This is patience measured in light hours. Now the story changes from what happened to what is still happening. Right now, humanity still has two aging witnesses outside the heliosphere, Voyager 1 and Voyager 2. They are not racing toward some dramatic destination marker we will reach next week. They are slowly crossing a region where the sun's influence fades and the galaxy takes over. And that region is not settled science. Researchers are still trying to understand how the background plasma emission is produced. They are still asking why the density changes the way it does. They are still comparing the rare, sharp whistles caused by solar eruptions with the weaker, steady hum that seems to sit underneath. The frontier is still being read line by line. Those sharp whistles are important too. When strong disturbances from the sun move outward through space, they can trigger clearer plasma oscillations. Those events act like sudden flashes of light in a dark room. They make the density easier to measure at specific moments. But the faint background emission matters even more, because it may let scientists measure the medium continuously, not just during lucky outbursts. That was one of the biggest scientific upgrades in this whole story. Before the faint background signal was understood, the map of interstellar density was sparse. Researchers only got solid clues when the sun happened to send out a useful disturbance. Now they may be able to track density more often. That is like going from a few snapshots to a slow, steady documentary. Did you know the real prize here is not the spooky sound, but the hidden map behind it? When a faint tone can tell us how crowded the space between stars really is, that is a different level of discovery. If that blows your mind, leave a comment with the word map, hit subscribe, and let me know if you want more stories like this. Voyager 1 gave researchers one set of clues, but one clue can still fool you. Maybe a finding is only true where that one spacecraft happened to be. Maybe it is caused by timing. Maybe it is some local weirdness. Voyager 2 helps beat that problem by offering a second path through the boundary, and the two paths were not identical. Voyager 1 crossed in 2012 at about 121.6 astronomical units. Voyager 2 crossed in 2018 at about 119 astronomical units. That difference matters because the Sun goes through an activity cycle of about 11 years, and the heliopause can move in and out like a breathing lung. So when the two Voyagers crossed at different places and different times, scientists got a kind of natural experiment. If both craft saw some of the same strange patterns, the odds went up that those patterns were real features of the heliosphere's edge. And that is exactly what happened with several major findings. The denser plasma, the transitional region, and the magnetic surprise all grew more believable. One of the cleanest lessons from Voyager 2 is that the boundary is not a single thin line with simple rules. NASA's own summaries say the spacecraft appears not to be in fully undisturbed interstellar space yet. Instead, it seems to be in a perturbed transitional region just beyond the heliosphere. That means the Sun is still affecting the environment there, even after the crossing. This is a huge deal for how we picture our place in the galaxy. We often imagine sharp edges because sharp edges are easier to understand. But nature likes gradients, pressure zones, overlap, and turbulence. The border around our solar neighborhood may behave less like a fence and more like surf at the beach. The wave breaks, but the water keeps mixing. That mixing also helps explain why a frequency out there is worth watching. Waves carry information. If the plasma is denser, compressed, or disturbed, the frequencies can shift. If a solar event passes through, the signal can flare. If the local interstellar medium changes, the tone may drift again. Each change is a clue from a place our bodies will never visit. And there is something almost eerie about how this clue reaches us. Voyager is not coming home with samples in a box. It is not dropping off rocks. It is just sending patterns in radio data. Across an almost impossible distance, a machine no larger than a small car is telling us, bit by bit, what the darkness feels like. The public often hears words like frequency and signal and immediately jumps to one question. Is somebody out there sending it? That is a human reaction, and an understandable one. But the deeper wonder here is that the universe does not need to be speaking on purpose to tell us things. Its structure speaks through physics. In this case, the voice is a language of charged particles and fields. A rise in pitch can point to higher density. A sudden burst can point to a shock wave from the sun. A quiet, narrowband tone can reveal ongoing plasma conditions. So the mysterious frequency is mysterious because it opens a door, not because it points to a secret civilization. Still, the mystery has emotional power because of where it comes from. Voyager 2 is so far away that the spacecraft itself feels almost like a myth. Yet it is real, it still exists, and it is still helping humans understand the first true coast between our star and the wider galaxy. That coast matters for more than curiosity. Cosmic rays are energetic and dangerous. Understanding how the heliosphere blocks them helps us think about space travel, astronaut safety, and even the long-term conditions around Earth. If we want humans to go farther into deep space, we need to understand the shield we are leaving behind. There is a personal angle too. Everything you have ever known has lived inside the sun's bubble. Every mountain, ocean, city, and heartbeat on Earth grew under the protection of this moving shell. Voyager 2 is giving us the first rough weather report from the other side. That turns a huge abstract idea into something almost intimate. Here is another detail people remember once they hear it. NASA estimates it could take Voyager 2 about 300 years just to reach the inner edge of the Oort cloud, and it may take around 30,000 years to fly beyond that wider gravitational realm. So even this brave old spacecraft, already beyond the heliosphere, is still at the beginning of a much larger outward journey. That scale can make you feel small, but it can also do the opposite. It can make human effort feel huge. We built something with 1970s tools that is still teaching us in the 21st century. Not because it is perfect, because it was built well enough and loved carefully enough to keep going. Now think about the mystery from the scientists' side. They expected colder, denser plasma outside the heliosphere. They found that, but also more warmth than expected, signs of compression, and a region not fully settled. They expected the magnetic field to show a clearer break. Instead, both Voyagers pointed to surprising alignment. They expected a border. They found a process. They expected a handoff. They found an argument between the sun and the galaxy, still playing out in motion. And inside that argument sits the strange frequency, like a thin line on an instrument screen proving that empty space is doing more than sitting still. What would you feel if you were the engineer seeing that data arrive after a 16-hour wait? Would you trust it right away? Or would you think the old machine was confused? If you would still bet on Voyager after all these years, drop a like, subscribe for more, and tell me whether you would trust the signal or question it first. One reason the Voyagers remain so powerful in the public imagination is that they do not feel finished. A completed mission sits in a museum. Voyager 2 does not. It is still out there, still moving, still crossing a region no human can reach anytime soon, still fading and reporting at the same time. That makes every new confirmed clue feel alive. There is also a quiet lesson here about how science really works. A headline screams that Voyager 2 found a mysterious frequency. Science answers more slowly. What kind of frequency? Under what conditions? How often? What can it measure? Is it local, temporary, common, or part of a larger pattern? That slower process is not weakness, it is strength. It is why NASA did not stop at "we heard something weird." Scientists compared instruments, compared spacecraft, compared dates, and compared models. They asked what they expected, what they found instead, and why the gap between those two matters. That gap is where discovery lives. If everything matched the prediction, you would learn less. But when the edge of the heliosphere turns out messier, warmer, denser, and more connected than expected, the whole picture of our solar neighborhood sharpens. Suddenly the sun is not just a star with planets, it is a moving system negotiating with the galaxy every second. And because of that, the Voyager story is not only about the farthest spacecraft, it is also about us. Earth sits deep inside the sun's bubble. If that bubble changes shape, strength, or leakiness over time, it affects the flow of radiation through our neighborhood. That matters for future probes, future astronauts, and maybe one day, future settlers far from Earth. There is a reason so many scientists remain obsessed with the interstellar medium. It sounds dry at first, almost boring, but it is the material between stars, the thin stuff that fills the galaxy, carries shock waves, holds magnetic patterns, and helps shape cosmic environments. Voyager is not just passing through emptiness, it is passing through the galaxy's skin and weather. And the frequency makes that invisible weather measurable. That is why the finding sticks in your mind. A hum in the dark is more than a dramatic phrase. It means the dark is not dead. It has pressure, motion, and texture, and a small machine from Earth has been sensitive enough to notice. We should also remember how little data this mission sends compared with modern technology. Voyager is not streaming high-definition video. It is whispering tiny amounts of information. Every bit is precious. Every result comes from careful decoding, patient checking, and a lot of trust in old engineering. That is part of what makes the discovery feel almost human. Voyager 2 is old, limited, and far from help. Its power is fading. Its instrument list is shrinking. And yet it keeps handing us clues from the edge of what we can physically touch. There is dignity in that kind of persistence. Right now, beyond the planets, beyond the old maps children learn in school, Voyager 2 keeps moving through a region where our ideas are still unfinished. It has already shown that interstellar space near the Heliopause is denser than expected from the inside view. It has shown that the boundary is active and compressed, and it has helped turn a faint frequency into a tool for measuring the unseen. Maybe the most beautiful part of this story is that the mystery did not vanish once it was named. Calling it a plasma wave emission does not kill the wonder, it deepens it. Now the question becomes, what shapes that emission? How does it change? And what else will it tell us as Voyager travels farther from the sun's wake? Because one day, if the signal shifts enough, scientists may learn where the local influence of our heliosphere truly fades. They may map more of the very nearby interstellar medium. They may understand better how the sun's bubble moves through the galaxy. And all of that can begin with a thin, unexplained tone that would have been easy to ignore. So when people say Voyager 2 detected a mysterious frequency beyond our solar system, the honest answer is both yes and not exactly. Yes, Voyager 2 helped confirm strange plasma behavior beyond the sun's protective bubble. Yes, that behavior includes frequencies that reveal the nature of interstellar space. But the real story is not a cosmic scream. It is a quiet measurement rewriting the map of our home. That is almost more unsettling than fiction, because fiction gives you monsters and endings. Reality gives you a border that leaks, compresses, shifts, and hums. Reality gives you a machine built before the internet that is still finding cracks in our understanding of the universe. And reality says the empty dark between stars is not empty enough to stay silent. If Voyager 2 suddenly went quiet forever tomorrow, it would still have changed space science for good. It showed us all 4 giant planets up close. It became only the second human-made object to enter interstellar space. It helped reveal that the Heliopause is a living boundary, not a simple line. And it turned faint frequencies into evidence that the galaxy around us has structure we can actually measure. But it has not gone quiet yet. That may be the most powerful sentence in this entire story. Not yet. Even as instruments shut down and power fades, the mission goes on. And as long as it does, every new data point from the dark carries the weight of first contact with a place no one has ever reached. So here's the question I want to leave with you. When you picture the edge of our cosmic home, do you imagine a wall, a shoreline, or a storm? Subscribe, turn on notifications, and tell me in the comments which one feels most true after hearing Voyager 2's story. And share this with someone who still thinks space is empty and quiet. Thanks for watching. I'm glad you came with me this far into the dark. I'll see you in the next one.